All right, let's jump right into it. Today, we're unpacking a massive engineering paradigm shift. I mean, as developers, we've all hit that dreaded VRAM bottleneck, right? It's brutal. But what if I told you that you could run a 30 billion parameter model natively on a consumer SSD? Literally zero need for 60 gigabytes of VRAM. That's exactly what we're looking at in today's explainer, how we are moving away from those heavy, dense, linear matrices and into the world of nonlinear point clouds. Here's our technical roadmap. We'll start with the VRAM bottleneck problem, look at moification and how we create point clouds, check out the SSD data mapping architecture, and then dive into SHD CCP lossless spatial compression. Finally, we'll cover dynamic routing and asynchronous inference, and see how this all completely redefines AI hardware limits. Okay, Section 1, the VRAM bottleneck problem. Let's start by exposing the inherent inefficiencies of traditional large language models. Honestly, processing linear transformer models the way we do right now, it's fundamentally broken. Think about it. When you prompt an LLM about quantum physics, calculating neural weights for cooking recipes is just a massive waste of sequential compute. Traditional models are basically loading these rigid, heavy matrix blocks layer by layer and just absolutely devouring your VRAM. But the alternative is a total game changer, nonlinear point clouds. By grouping parameters by semantic activation, we only load what we actually need straight from the SSD. Moving to Section 2, moification, creating point clouds. To fix that sequential nightmare, we have to transition to a completely new architecture. So the mathematical process we use to build this topographical network is called moification, or sometimes you'll hear it called sparse upcycling. This technique is absolutely crucial. It's used to completely shatter those massive, rigid feed-forward network layers into highly manageable, semantically specialized expert splinters. So instead of dealing with one giant, heavy matrix, you end up with thousands of agile, specialized little fragments. Here's how that actually builds out mathematically. First step, we apply a k-means clustering algorithm to the columns of the model's up and down projection weights. Step 2, we group the vectors that mathematically fire together on similar topics into semantic clusters. And finally, step 3, we run a conversion script to write that data out as indexed binary blocks. Basically, you end up with a highly organized point cloud where semantically similar weights live right next door to each other. All right, Section 3, SSD data mapping architecture. So now that we have our point cloud, how do we physically map it onto standard consumer hardware? We use a blocked sequential layout. We partition the SSD into exact 50 megabyte sectors. So file offsets and hashes map directly to precise thematic clusters. For example, offset 0 holds logic and syntax. You jump to offset 0x032 and boom, you find math and primes. We're essentially turning the SSD into a highly indexed map instead of a sequentially read book. You aren't reading 60 gigs from top to bottom anymore. You're jumping directly to the exact data you need. And get this, 12 bytes. That is the magic number here. The brilliance of this architecture is that a tiny 12-byte entry hash is the absolute only key you need to instantly locate and pull a massive 50 megabyte data block. It's incredibly efficient. Which brings us to Section 4, SHD-CCP, lossless spatial compression. Mapping is great, but to store these topographical networks efficiently, we need some serious compression. The thing is, standard compression just flat out fails on spatial AI data. Traditional methods like Z-standard or LZ4, they hit a brick wall on 3D point clouds, giving you less than a 5% compression ratio. Draco gets you 10-to-1, sure, but it completely destroys raw fidelity. And neural methods? They hallucinate, which is obviously a complete catastrophe for neural weights. But SHD-CCP Concept Alpha? It delivers a massive 8 to 50-to-1 compression ratio at 99.99% fidelity, all with an ultra-low 5-millisecond latency. It's a wild. So how does it actually pull this off? SHD-CCP, which stands for Symbolic High-Dimensional Context, by the way, overcomes the Shannon limit by assuming the real data is multimodal, not just a single entropy model. It uses mathematical constants like the golden ratio phi and tau to map out spatial relationships. Using an equation of sum of 1 over h times sine of phi times h times t, and leveraging 11 specific block classifications like sparse 0, delta, and shuffle, it can literally take 50,000 data points and compress them down into a simple 12-byte seed plus a tiny 4-kilobyte residual. And despite that extreme level of compression, when it reconstructs the spatial data from that 12-byte seed, it does so with a staggering precision of 0.001 millimeters. The accuracy is just phenomenal. Let's move to Section 5, Dynamic Routing and Asynchronous Inference. The data is mathematically compressed and geographically mapped on the SSD, so let's look at the runtime environment. To really grasp this, you need a completely different mental model. Just forget the idea of reading a model from cover to cover. Instead, think of inference as a search beam or scanner navigating a 3D topographical map. You navigate the space, and you extract only what is contextually necessary for that specific moment.
At inference time, the whole process is incredibly streamlined. Step 1, the gating network router analyzes the input token to figure out the topic. Step 2, it generates that corresponding 12-byte hash. Step 3, your asynchronous mmap engine checks the ultra-slim .index lookup table. And step 4, the engine jumps directly to the exact 50-megabyte block on the SSD and pulls it into the CPU cache. The crazy part? While it's processing that block, it's already calculating and asynchronously firing the request for the next 12-byte jump.
Because you're jumping via that index file, there is absolutely zero search delay. You are effectively getting O of one-time complexity. And the rest of your massive 60-gigabyte model, it just sits there, completely untouched on the drive. Finally, Section 6, Redefining AI Hardware Limits. Synthesizing all these technical breakdowns really reveals a complete redefinition of what consumer hardware can accomplish.
This is exactly why this matters for every single developer watching. We're shifting the primary processing load from brute force raw compute to intelligent data filtering. By doing this, we completely eliminate that 60-gigabyte VRAM bottleneck. You can now run powerful 30 billion parameter models locally on standard hardware. We're talking a basic Ryzen 5 laptop or even on a smartphone using Termux. Plus, because it's a point cloud, you can run parallel observers. These are asynchronous processes that jump to different areas of the SSD to check logical consistency all at the same time, without ever blocking the main compute thread. It's a real game changer.
Which brings us to our final thought for this explainer. This breakthrough in spatial compression and topographical routing forces us to ask a really serious question. If a 30 billion parameter model can run without search delay directly off an SSD via nonlinear topologies, how quickly will you adapt your own AI architecture to abandon the linear VRAM bottleneck? Thanks for joining me on this explainer. Start rethinking those data structures, and I'll catch you next time.